everybody, this is your ma'am Akshata and I would like to welcome you all to the session today. Well, in our session today, we are going to talk about redox reactions. But before we dive into redox reactions, we need to understand what exactly is redox reaction, right? And there are a certain few concepts that we need to learn about. So let's see what all are we going to talk about in our session today and what our session really comprises of. So in our session today, we shall be talking about redox reaction. What exactly is redox reaction? All right. After we are done with the discussion of redox reaction, we will then talk about oxidation state. We will then talk about oxidation state. What is an oxidation state? How do we calculate it? And finally, we shall be discussing about balancing. Balancing of reactions. So without further ado, let's just get into the session. So what exactly is a redox reaction? See, redox reaction is of vital importance to us. That is the reason why we are learning about it. But what does it really comprise of? So let me tell you that redox reaction comprises of oxidation as well as reduction. Now, from what you have previously learnt in your 10th grade, that oxidation is a reaction in which oxygen is added or hydrogen is removed, right? That is what you have learnt in your 10th grade. But in your 11th grade, a new term comes into picture, which is with respect to electrons, When electrons are lost, okay, when an element is losing electrons, it undergoes oxidation, right? And that causes increase in the oxidation number or the oxidation state. That causes an increase in the oxidation number. So you can see over here like that to magnesium and oxygen is added, magnesium oxide is formed, and you know that this is a oxidation reaction. Removal of hydrogen also to hydrogen sulfide. When we reacted with chlorine, you get hydrogen chloride and sulfur. Now here chlorine is the one which is undergoing reduction and sulfur is the one which is undergoing oxidation, right? Increase in the positive charge, that is Fe plus 2 is undergoing oxidation to Fe plus 3 by the loss of electrons. As a result, there is an increase in the oxidation number. Thereby, removal of electrons is also known as oxidation. Removal of electrons is also known as oxidation. In addition to this, when an electronegative element is added, even that causes an increase in the oxidation number, and that is also oxidation, right? So that is about oxidation. So what is the reduction? The exact opposite of oxidation stands true for reduction. So you can either learn oxidation or reduction individually based upon what works for you, and the opposite stands true for the other. So in oxidation, as we have learnt, that addition of oxygen is oxidation, removal of hydrogen is oxidation. In reduction, addition of hydrogen is oxidation. Addition of hydrogen is reduction. Okay, addition of hydrogen is reduction. Removal of oxygen is reduction. This is something that you have already learnt in your 10th. How is it different? Well, now we'll understand it with respect to electrons. When electron is added to an element, or I would rather say when an element accepts electrons, it undergoes reduction, as a result of which there is a decrease in the oxidation number. And that is nothing but reduction. So as you can see, removal of oxygen or any other electronegative element. See, what did I tell you for oxidation? That if an electronegative element is added, even that causes an increase in the oxidation number. So if you remove an electronegative element, it will cause a decrease in the oxidation number, is it not? That is why removal of oxygen or any other electronegative element is known as reduction. Then addition of hydrogen, that is to sulfur, when you are adding hydrogen, it is undergoing reduction by forming hydrogen sulfide. Decrease in the positive charge, that is Fe plus 3, by the gain of electron. Okay, it is turning into Fe plus 2. That is, the oxidation is now undergoing a reduction. And addition of electron is nothing but reduction. Now the question is, ma'am, how do we calculate this oxidation number? Okay, oxidation number, but how do we know? How do we learn? Or do we calculate? You have multiple questions right now running through your head. Don't worry. We can calculate it, right? So we will get there. But now let's understand. Now, since we have understood oxidation and reduction separately, as you know, redox is nothing but, it is the combination of reduction and oxidation. So you have learned reduction and oxidation separately. Let's now learn redox. Let's now learn redox. Okay. Now, the modern idea of oxidation, as I told you, the modern idea of oxidation is nothing but de-electronation. It is de-electronation. Okay, that is zinc is losing electron, de-electronation. Okay, any metal losing electron is nothing but oxidation. Similarly, when you talk about reduction, any element gaining electrons is reduction. Yes, we have learnt the modern idea, we have learnt what we have understood in the 10th grade, and we have understood that reduction and oxidation together give rise to redox reaction. So, let's now understand what exactly redox reaction is. See, beta, let me tell you one thing. Reduction does not take place individually, or I would rather say oxidation does not take place individually. When oxidation takes place, reduction also happens simultaneously. And when reduction takes place, oxidation also happens simultaneously. That is, both reduction and oxidation go hand in hand. Let me tell you the reason why. Now, if an element is losing electron, now the electron can't keep wandering about itself, right? So the element in the vicinity will gain the electron. So what is happening? The element that is losing an electron is undergoing oxidation. But the other element which is accepting the same electron is undergoing reduction. That is why oxidation and reduction goes hand in hand. They take place simultaneously. And that is what is written over here. Many chemical reactions involve transfer of electrons from one chemical substance to the other. These electron transfer reactions are known as oxidation, reduction, or redox reaction. Or those reactions which involve oxidation and reduction both simultaneously. They go hand in hand, they work parallelly, they go simultaneously. Such reactions are known as oxidation reactions. Another definition for this is those reactions in which increase and decrease in oxidation number, of same or different atoms occurs is known as redox reaction. That means we are learning about the fact that oxidation reduction takes place simultaneously, right? One element undergoes reduction and it ends up oxidizing the other. How? By gaining the electrons from the other. Now, when you come across these terms, you also need to know what oxidation state is and how do we calculate it. See, oxidation state of an element or of an atom. Okay, oxidation state of an atom in a molecule of ion is the hypothetical or real charge present on the atom due to electronegativity difference. The charge that is present on the atom by the virtue of electronegativity difference is known as oxidation state, right? Oxidation state of an element in a compound represents the number of electrons lost or gained during its change from free state into that of combined state. That is when it turns into a compound. So this is about oxidation state. Now, some important points concerning oxidation number. Okay, some important points concerning oxidation number. So what are these important points? What are these important points? And how do we try to understand it? How do we try to understand it? So as we are already aware, as we are already aware, that oxidation number or oxidation state. Okay, oxidation state and oxidation number, I'm using these two simultaneously. Do they mean the same? Are they different? Well, they are different. They are different. How are they different, beta? How are they different? When you talk about oxidation number, okay, it is the charge of the central atom of a coordination complex. In a coordination complex, we talk about oxidation number. Oxidation state is the number of electrons that a particular atom can lose or gain. Okay. Now, you have not come across coordination chemistry yet, but you will see that many a times these two words are used inevitably as synonyms, but they don't really mean the same. Oxidation state basically talks about the number of electrons an element can gain or lose. Right? So oxidation state is what we will try to focus on over here. It is used, how do I say, synonymously, but you need to know that oxidation number is strictly for coordination complexes, about which you shall be learning in 12th grade. All right. So now how do we calculate the oxidation state? Now see beta, what happens is electronegativity values of no two elements are same. You need to understand that no two elements have the same electronegativity value. No, they will not. There will be some difference. Some difference or the other, and based on this only, we have decided which is the most electronegative element, which is the least electronegative element. You are already aware that metals are electropositive. That means they have the least electronegativity. Non-metals are electronegative. That means they have the least electropositivity. Now, what is electronegativity? The tendency to pull the electrons towards itself is known as electronegativity, right? That causes dipole in the particular molecule. But let's not get into that. What you need to understand is that when an electronegative element is added to a element, any element, let's say an electropositive element, what is it going to do? It is going to pull the electrons of the electropositive element, make it more, increasing its oxidation state. So when an electronegative element is added, it causes oxidation. Why? Because it increases the oxidation state of the element it is attached to. All right. So what you need to know is electronegativity values of no two elements are the same, beta. No two elements are the same. Phosphorus is more than hydrogen, carbon is more than hydrogen, sulfur is more than carbon, okay, chlorine is more than nitrogen, and oxidation number of an element may be positive or negative. It may be positive or negative. Oxidation number can be positive, it can be negative. Yes. Then oxidation number may be 0 for whole number or fractional value. It can be 0. It can be 0. That is for nickel, it is 0. It can also be fractional value, that is N3H. It can be fractional value also. Alright, it can be fractional value also. That means oxidation number can be 0. It can be positive. It can be negative. It can also be a fraction. It can also be a fraction. Now, oxidation state of same elements can be different in same or different compounds. Now here, in sulfur, hydrogen sulfide, the oxidation number here is -2. In H2SO3, it is +4. In H2SO4, it is +6. Ma'am, how do we calculate it? I'll tell you. Don't worry. One thing at a time. Just understand the facts first, that the oxidation number for the same element, the oxidation state of the number of the same element can vary in different compounds. It is not necessary that it will remain the same through and throughout. No. Okay. And some helping rules for calculating oxidation number. Now, what are some helping rules to calculate oxidation number? Now, understand, homoatomic molecules, that is when two similar molecules are put together. What have we understood? That the oxidation state that is there, the oxidation number that is there, that is because of the presence of an electronegative element. That means there needs to be electronegativity difference for an increase or decrease in the oxidation number. right? But for homoatomic molecules, the oxidation number is 0. Why? Same element, no? That means there is no difference in electronegativity. That is the reason why it is 0. That is the reason why it is 0 beta. So look at this. When A is there, it is going to be 0. For example, Cl, Cl, the oxidation number 0 in both the cases, right? Hydrogen, hydrogen, 0 in both the cases. Why? The same element is attached. Same element is attached. Now, for heteroatomic molecule, now if there is a heteroatomic molecule, then there is going to be a change. Then there is going to be a difference in the oxidation state, because electronegativity difference comes into picture. Beta. Now, the oxidation state of an element in its free state is always 0. In the free state, the oxidation state of the element is 0. 0. Hydrogen gas, 0. Chlorine gas, 0. Bromine water, 0. 0 is the oxidation state. Oxidation state of atoms present in homoatomic molecules is also 0. That is H2 0, O2 0, N2 0, P4 0, S8 0. It is 0, 0, 0. Now, oxidation state of an element in any of its allotropic forms is also 0. Because allotropic form is nothing but the purest form of that particular compound, right? Right? Allotrope is nothing but, see, carbon exists as graphite, it exists as diamond, but in all these cases, carbon is attached to carbon molecules only, no? So there is no electronegativity difference. So the oxidation state automatically becomes 0, right? Now, oxidation state of all the components of an alloy is 0. Now, this is important. Of an alloy is 0. Next, in complex compounds, oxidation state of some neutral molecules is also 0. In complex compounds, when you will be doing coordination chemistry next year, you will come across certain few ligands. You will come across certain few ligands and their oxidation state is 0. What are those ligands? Carbon, carbonyl group, nitrosyl group, amine, aqua, that is water. All of these, it is 0. Do we have to learn about this right now? No. This information will come handy next year. That is when you will be doing coordination compounds in your 12th grade. Now, the oxidation of fluorine in all its compounds is -1. This is something you need to know. Fluorine in all its compounds is -1 because fluorine is the most electronegative element. Fluorine is the most electronegative element to be present. So it has to be -1. Then oxidation state of 1A and 2A. Now what is 1A? 1A is nothing but your alkali metals. Alkali metals, that is the lithium family. And 2A is nothing but your alkaline earth metals. Beryllium family. Okay. So for 1A it is +1 and for 2A it is +2 respectively. That's that. Alright. Oxidation state of hydrogen in most of its compound is in +1. But when it is in metal hydrides, it is -1. What are the metal hydrides? Sodium hydride, lithium hydride, calcium hydride, magnesium hydride. In the metal hydrides, it is +1. Hydrogen is +1. But when it reacts with metal hydrides, now the problem is metals are electropositive, beta. Right? If they are electropositive, what happens? If they are electropositive, what happens? They tend to lose their electrons very easily. Now, hydrogen in front of metals is not that electropositive. That is why -1 is its oxidation state when with metal hydride. Now, oxidation state of oxygen in most of its compounds is -2. This you are aware of, but the exceptions you need to know. In peroxides, it is -1. Peroxide, that is when O is linked like this. Superoxides, it is -1/2. Superoxides -1/2. It forms superoxides with alkali earth metals. There it is -1/2. ozonoid. In ozonoid, 3 ozone molecules are there, na beta. 3 ozone molecules are there, so minus 1 by 3. And only when fluorine is there, the oxidation state is plus 2. The reason being, beta, fluorine is way more electronegative than oxygen. Fluorine is way more electronegative than oxygen. That is why with fluorine, it ends up having plus 2 as its oxidation state. Now that you have already learnt about, the various oxidation states, how to calculate them, let's do a certain few questions. Before we dive into oxidizing agent and reducing agent, and before we dive into balancing. Let's do a certain few questions. Okay, so what will be the KMnO4? Now, what is the oxidation state of manganese? Now, how do you do this? Now, the element whose oxidation state you're trying to find, okay, let its oxidation state be X. Okay, now on this entire compound, is there any charge? No. That means it is neutral. All its charges are balanced. That means the oxidation state of potassium plus manganese plus 4 oxygen is nothing but it adds up to 0. That is why there is no charge on this compound. What is the oxidation state of potassium? Plus 1. Why? Alkali earth element plus manganese, I don't know. Let's call it X. Plus oxygen minus 2 is equal to 0. So X minus 7 is equal to 0. X is equal to plus 7. This is the oxidation state of manganese in KMnO4. This is the oxidation state of manganese in KMnO4. Ma'am, any other example that you have? Let's take another example. SO4 minus 2. SO4 minus 2. Now let's try to find out the oxidation state of sulfur. But the problem is, beta, on this entire entity, there is a negative charge present. That means the charges are not balanced. That means the charge of sulfur and oxygen, the oxidation state of sulfur and oxygen, after addition gives rise to minus 2. It is not 0. So let's take the oxidation state of sulfur to be X plus that of oxygen. 4 into minus 2 is equal to 0. No, minus 2. The overall charge on this entity is minus 2. Okay. So their charges will add up to minus 2. So X minus 8 is equal to minus 2. X is equal to plus 6. X is equal to plus 6. X is equal to plus 6, beta. Is this clear? Let's do another molecule. CrO5. Now you will be thinking, ma'am, chromium X. Okay, so that means this becomes minus 10 is equal to 0. So plus 10 is the charge on chromium. No, that's why you're wrong. Now chromium happens to have a structure. It is known as butterfly structure within this molecule, and the structure goes like this. You see? Now here it is going to be minus 2, but you see oxygen-oxygen linkage is there. Minus 1, minus 1, minus 1, minus 1. Now this entire molecule is supposed to be electrically neutral. That means the charges of these oxygens will be balanced by chromium. So minus 2 plus minus 1 plus minus 1 plus minus 1 plus minus 1 total adds up to minus 6. Thereby the charge on chromium becomes plus 6. That is X plus 4 into minus 1 plus 1 into minus 2 is equal to 0. Excuse me, guys. So x is equal to minus 6 is equal to 0, x is equal to plus 6. X is equal to plus 6. I hope this is clear. I hope this is clear. Let's do another one. Let's do another molecule. Tribromo octa oxide. That is nothing but Br3O8. Right? Now you'll be saying, ma'am, for bromine it is going to be 0 because bromine is attached to another bromine molecule. Wait a minute. Bromine is also attached to oxygen molecules. You're not supposed to forget that. Bromine is also attached to oxygen molecules. So what is the charge going to be on each of bromine? So here it is going to be minus 2, minus 2, minus 2. Now the charge of this will be balanced by bromine. This bromine will have no charge because same, no electronegativity difference. So the charge on this is plus 6. Now minus 2, minus 2. So the charge on this becomes plus 4. It needs to be balanced. Minus 2, minus 2, minus 2. The charge on this becomes plus 6. So ma'am, what is going to be the oxidation state? The oxidation state for the bromine in this one is going to be the average of all of 3. That is nothing but plus 6 plus 4 plus 6 divided by how many bromines are there? 3. That is nothing but 16 by 3 is the oxidation state of bromine. This is how you get your fractional oxidation state. This is how you get your fractional oxidation state, beta. This is how you get your fractional oxidation state. Clear? Clear? Clear, beta? Okay? All right then. Now that we are done with how to calculate the oxidation state. Okay, let's now try to understand what exactly is this oxidizing agent, reducing agent, what is it? Okay, let's understand. Oxidizing agent or oxidant. While you read the definition, I just want to share something with you. Oxidizing agent, an agent that helps in oxidizing others. Right? An agent that helps in oxidizing the other molecule. Now, what did I tell you? Oxidation and reduction takes place simultaneously. So, if an element is oxidizing other, that is, it is taking up the electrons of the other, allowing it to oxidize, right? So, the one that is taking up the electrons is undergoing reduction, right? Hear me out again. Hear me out again. Okay. An element is undergoing oxidation. Oxidizing agent will allow an element to undergo oxidation. What is oxidation? Loss of electrons. Now, these electrons will not lurk around, no, the electrons that are lost. This oxidizing agent that is there, it is helping in oxidation by taking the electrons. Now, what is happening is, it is helping in oxidation by taking up the electrons. But in turn, itself is undergoing reduction because it is taking up the electrons. That is what is written over here. Oxidizing agents are those compounds which can oxidize others and reduce itself during chemical reaction. That means you can say an element that is undergoing reduction is an oxidizing agent. Now, if if you understand this, reducing agent is not that big of a deal. Those reagents in which for an element oxidation number decreases or which undergoes gain of electrons in a reduction reaction or redox reaction are termed as oxidants. Example, KMnO4, K2Cr2O7. Now you must be thinking, ma'am, why these elements? What is the reason? There's a reason for this also. Everything has a reason. Why is it that these elements are only acting as oxidizing agents? Why not nobody else? What is the reason? Let's see. But before we get there, let's first understand what is reducing agent. Now, if oxidizing agent is the one which is, which is helping in oxidation of the other element by itself undergoing reduction, that means a reducing agent is the one that is allowing the other element to undergo reduction by itself undergoing oxidation. That is what is written over here. Reducing agents are those compounds which can reduce other and oxidize itself during the chemical reaction. Those reagents in which for an element oxidation number increases or which undergoes loss of electrons in a redox reaction are termed as reductants. The examples are given over here. Note, there are some compounds which can work as both oxidizing agent and reducing agent. Ma'am, how are we going to then understand? How is it that which one is oxidizing, which one is reducing? What is happening? Calm down. So far we learnt about oxidation state, did we not? Trust me, it circles back to that. How? See beta, if an element is in its highest oxidation state, can it further undergo oxidation? No. No, right? Because it is at its highest oxidation state, but it can undergo reduction. That's the only option it has. So elements which have the highest oxidation state, elements which are in their highest oxidation state, act as very good oxidizing agents because they themselves are willing to undergo reduction. Okay? Because they are themselves willing to undergo, reduction. Now the next question is, ma'am, then what about minimum oxidation state? Now minimum oxidation state, they cannot get reduced more than that, no? But they can undergo oxidation. That is why they act as reducing agents. They happily let go of their electrons and undergo oxidation. Okay, ma'am, this is clear. But then you said that there are elements that act as both oxidizing agent and reducing agent. Now there are elements that are in their intermediate oxidation state. They can undergo either oxidation or reduction. The intermediate, no? They are in between. They can jump here, they can jump there. Right? So when I talk about maximum oxidation state, its oxidizing agent KMnO4 is K2 Cr2O7 is, okay, HNO3 is minimum oxidizing, okay, minimum. In minimum HNO2 is there. Intermediate SO2, NO2, etc. Alright, beta? Alright? So this is about how to find the oxidation state of the central atom and how it dictates whether it is going to act as a reducing agent or a oxidizing agent. Now there are different types of redox reactions. Yes. Just like redox reaction is there, it has different types. Redox reaction is a type of reaction. It again is of different types, of which what is there in your syllabus is disproportionation reaction and comproportionation reaction. What is disproportionation reaction? When a single element, you can relate it with divergent, okay? Single element is there in a particular oxidation state. It is undergoing reduction. The same element is undergoing reduction and is undergoing oxidation. That is disproportionation reaction. That is disproportionation reaction. What is comproportionation reaction? Now, comproportionation reaction is like, it is like convergent. Comproportionation reaction, that is element in the reactant. Okay, there is one reactant and that only there is, the element is in two oxidation state. One is in a, I will rather say like this. In low oxidation state, in high oxidation state, they together give rise to a single oxidation state. Single oxidation state. So when you look at disproportionation reaction, beta, disproportionation reaction, the best example for this is Cl2 giving rise to Cl minus plus ClO3 minus. Here the oxidation state is 0, here it is -1, and over here it is x plus minus x is equal to plus 5. So the same element is undergoing over here, if you see, it is undergoing reduction. And over here, if you see, it is undergoing oxidation. It is undergoing oxidation. This is about disproportionation reaction, beta. This is about disproportionation reaction. So, ma'am, what about comproportionation reaction? But before we go there, here have a look at some of the disproportionation reactions. Have a look at some of the disproportionation reactions, please. These are some of the examples. These are some of the examples of disproportionation reaction. Single element, -1, -2, 0, 0, -2, +2, 0, -1, +1, -1. You see, it is undergoing both reduction and oxidation at the same time. This is disproportionation, divergent behavior. Okay, single oxidation state is there, it is undergoing both reduction and oxidation. Right? Now, over here are some important reactions that you will come across, beta. Some important reactions that you will come across. Let's now talk about comproportionation reaction. Comproportionation reaction. Okay, here nitrogen is in -3 oxidation state and here in +3 oxidation state, but together they give rise to a single oxidation state. That is, it is undergoing reduction and oxidation at the same time. So it is undergoing from one, reduction is also undergoing, it is undergoing reduction, it is also undergoing oxidation to give rise to a single oxidation state. Single oxidation state. Single oxidation state. Now, how do we balance a redox reaction? How do we balance a redox reaction? It is in two methods, beta, ion-electron method and oxidation method. Let's talk about ion-electron method. Now, this ion-electron method, it takes place either in the acidic medium or in the basic medium. It takes place either in the acidic medium or in the basic medium. Acidic medium or in the basic medium. Okay. And there are a certain set of rules that are supposed to follow. But I want to give you an example for this. The example that I'd like to give you guys is, there are a set of rules. Please have a look at them first. Okay, this method was given by Jeeton Lomav in 1972. Okay, so basically, I'll tell you what it is basically stating over here. See, in acidic and basic medium, certain steps are same. Only when it comes to balancing the hydrogen, the steps changes. How, ma'am? I'll tell you. what we do is we write the ionic reaction, whatever ionic reaction is there, be it an acidic medium or basic medium. Then obviously redox reaction is taking place. So reduction part and oxidation part, you'll separate. You'll write the reduced, you'll divide the page into two columns. You'll write the oxidation on one side, reduction on the other side. After you have done that, the oxidation reaction on one side and reduction reaction on the other side, which is taking place in the redox reaction, what you will do after that is you will balance all the elements other than hydrogen and oxygen. You will balance all the elements other than hydrogen and oxygen. Once that is done, what you will do is you will balance the oxygen. Now the question is, how will you balance the oxygen? Now, in both in the oxidation and reduction side, you will balance the oxidation. You'll balance the oxygen. How will you balance the oxygen? By adding water molecule H2O on the side where oxygen is less. On the side where oxygen is less. Okay, ma'am. Oxygen is now balanced. Now you have introduced water molecule, no? You have to now balance the hydrogen. For acidic medium, it is sorted. The number of hydrogen molecules, wherever it is deficient, you add the number of deficient molecules of hydrogen as there in the side where the number of deficient molecules are there in the form of H plus ions. In basic medium, what you do is you first add OH on the side where hydrogen is maximum, and then the total number of water molecules on the side where hydrogen is deficient. And then you subtract the water molecules. After this is done, you then balance the electrons. Once that is done, what do? You add the reduction and oxidation reactions, and tada, you will get your reaction. Balanced reaction. Let's try to do one. Okay, let's try to do one. Take down beta in acidic medium. In acidic medium, let's take I2 reacts with NO3 minus to give rise to, this H plus indicates acidic medium. I2 reacts with nitrate to give rise to IO3 minus and NO2. IO3 minus and NO2. Now tell me, what is the oxidation state of iodine? Quick. Oxidation state of iodine. So over here it is 0 beta. Here it is plus 5. 0 plus 5. That means nitrogen is the one which is undergoing reduction. Well, clearly it is. Here it is plus 5. Here it is plus 4. Now you can see that iodine is the one which is undergoing oxidation. So this is the half reaction where oxidation is taking place, and this is where reduction is taking place. Now you will divide your page into two columns, and on one side you will write oxidation, on the other side you will write reduction. Clear? Now for iodine, what you're going to do is I2 is giving rise to IO3 minus. This is your oxidation. In reduction, what is happening? NO3 minus is giving rise to NO2. Fine. This has been done. Now you will balance this is the first step, okay? You have written the half cell reaction. And now you will balance the element other than oxygen and hydrogen. So there are two iodines over here, only one. So you are going to balance. I2 gives rise to 2IO3 minus. Over here, there is no change. You will still copy it as it is, NO3 minus, so that you are aware of all the steps. You will not miss out on any. Once this is done, now you will balance the oxygens. You will balance the oxygens. How do we balance the oxygens? By adding the water molecules on the deficient side. Now, how many oxygens are there over here? Ma'am, 3. No, 6. 2 into 3, 6. So, what you're going to do is, you're going to add I2 plus 2 into 3 is 6, right? 6H2O gives rise to 2IO3 minus. Over here, 3 oxygens, only there are 2. So, you will add NO3 minus. On the deficient side, you will add the number of water molecules with respect to the number of deficient oxygens that are there. Clear, ma'am, clear. Now, to balance hydrogen, you will add H plus. You will add H plus. Where will you add H plus? On the side where hydrogen is less. So, here there are 6 into 2, 12 hydrogen. Here 0. So, you will add I2 plus 6H2O gives rise to 2IO3 minus plus 12H plus. Over here there are 2 hydrogens, 0 over here. So, NO3 minus plus 2H plus gives rise to NO2 plus H2O. Now you check. All your elements are balanced? Yes, ma'am, they are balanced. But what is not balanced? The charges. You have to now balance the charges, beta. You have to now balance the charges. How? There are 2 negative charges, 2 IO3 minus, so 2 negative charges. 12 positive charges. So 2 negative, 12 positive. Is it balanced? No. So you need to add more negative charge. How will you add? 10 electrons. An electron method. No. Add electrons. What is there in that? Now on the other side, you see there is 1 electron, 2 protons. So I'll add 1 more electron over here. Now the charge is balanced. Ma'am, is that it? No, it's not. You have to now balance the charges. How many electrons are there over here? 10. Over here, 1. Multiply this entire thing into 10 to balance the electrons. As a result, now you will write the combined equation, okay, half cell reactions. So you will write I2 plus 6H2O gives rise to I2 plus 6H2O gives rise to 2IO3 minus 2IO3 minus plus 12H plus 10 electrons. Okay, this is the oxidation. Oxidation half cell. Now let's write the reduction half cell reaction. Reduction half cell reaction, which is nothing but 10NO3 minus plus 10NO3 minus plus 20H plus 10 electron gives rise to 10 electron gives rise to 10 NO2 plus 10 NO2 plus 10 H2. Now what you're going to do is you're going to balance. How are you going to balance? 10 electrons cancel, 10 electrons cancel. 12H plus 20, that makes it 8. 6H2O, 4H2O. Now your reaction, balanced reaction is I2 plus 10NO3 minus gives rise to plus 8H plus gives rise to 2IO3 minus plus 10NO2 plus 4H2O. This is how you do it. This is how you do it. All right. In the basic medium, what you do is, in the basic medium, beta, what is different is, you see the fourth step, there's a difference in the fourth step only. Okay, there's a difference in the fourth step only. In basic medium, what is the difference? In basic medium, all steps are same. Fourth step differs. The fourth step is what is different. How is it different, beta? To balance hydrogen, you add OH minus to the side, to the same side, okay, to the same side, and H2O. Okay, you add H on the same side. Okay, to balance hydrogen, you add OH minus to the same side where H2O is more, and H2O on the opposite side. So what you do is, to balance hydrogen, we add OH minus to the same side where hydrogen is more, and the same number of water molecules as that of OH. The same number of water molecules as that of OH on the opposite side. That is where hydrogen is deficient. You can try this, bachas. Only the fourth step is different, rest all is the same. Only the fourth step is different, rest all is same. Now when we talk about oxidation number method, how do we do this? See beta, there is something known as N factor. We calculate the N factor, okay, and then the reverse of the N factor is nothing but the molar ratio. But how do we calculate the N factor? Select the atom and oxidizing agent whose oxidation number decreases and indicate the gain of electrons. See, gain of electrons. Now see, we see that when oxidation is happening, the oxidation state is increasing. When reduction is happening, the oxidation state is decreasing. But in N factor method, that is in the oxidation number method, we show the increase in number of electrons as a positive sign. The positive sign is only to show the increase of electrons. This is nothing but reduction, and the decrease in number of electrons as a negative sign. This positive sign and negative sign is only and only to indicate, it is only and only to indicate the decrease in the oxidation state, beta. It is only and only to indicate the decrease in the oxidation state, nothing less, nothing more. To indicate the decrease in the oxidation state. Okay? Let's take an example for this. Okay? Let's take an example for this. CuO plus NH3 gives rise to CuO plus NH3 gives rise to Cu plus N2 plus H2O. Quickly calculate the oxidation states. Quick. Quickly calculate the oxidation states, beta. Quickly calculate the oxidation states. Now here it is in +2 state. Okay, and nitrogen is in -3 state. Here 0, here 0. That means here copper is undergoing It is undergoing what? Reduction. How? By the gain of 2 electrons. So plus 2 is what we write. Because plus is to indicate gain. Now here nitrogen is undergoing oxidation. How? By the loss of 3 electrons. Minus 3. This is just to indicate that gain and loss has taken place. Now how do we write it? The ratio, the n factor ratio. The n factor ratio of copper oxide is to NH3 is plus 2 is to 3. You don't have to mention in ratios, you don't have to mention the signs, beta. So molar ratio is going to be the reverse of this. 3 is to 2. So when you balance this equation, you will write 3CuO plus 2NH3 gives rise to. Now you can balance 3Cu plus 2, plus N2 only, plus 3H2O. This is how you go about it. All right. That is what they're saying. Now cross multiply the oxidizing agent by the number of loss of electrons and reducing agent by the number of gain of electrons. That is what is done over here. In order to balance oxygen atoms and hydrogen, that is water molecules to the side deficient in oxygen, and balance the number of hydrogens by adding H plus ions in the hydrogen side. That's it. Now what is the application of this oxidation number? We are focusing so much on oxidation number. What is its application, ma'am? Ma'am, what is its application? It is very simple. More is the oxidation number, beta. More is the oxidation number. More acidic is the nature. More acidic is the nature. Less is the oxidation number. Basic is the nature. This is one application, that is to compare the acidic and the basic strength. The second is the order of acidic strength in HClO, HClO2 and HClO3 is like this. Clear, beta? So this is where they have given you the oxidation states, highest and the lowest, right, to determine the oxidizing and reducing nature of substances. See, now if they have given the highest and the lowest, it is easy for you to determine. See, if highest oxidation state is there, it can only undergo reduction, it will act as a oxidizing agent. If lowest oxidation state is there, it can only undergo oxidation, so it will act as a reducing agent, right? So this is another application of it, right? They have given you the maximum oxidation state numbers. So is the case over here. And with this, kids, we have come to the end of our session. With this, we have come to the end of our session. We have understood what redox reactions is. We have understood how to calculate oxidation state, how to calculate, the balancing of reactions. Everything has been done in detail. If you have any doubts, please do reach out to me. Let me know in the comment section and I'll get back to you. So until we meet next, keep smiling, keep revising and stay healthy. Bye-bye.